All right, today's going to be fairly quick because we just have 2 more examples of these related rates to go over, and then I want you to work on some homework problems either from the related rate section or the implicit derivative section in preparation for our test next week. So looking at the schedule, I know up there yesterday it said board day, but looking at the things that we have left to cover in the unit, we actually are going to have our first free response day.
Let's go.
Yes, so we're going to take a look at, and the problems, like the related rates that we've been doing so far, lend themselves very well to free response type questions, so we're going to spend our time tomorrow looking at those. Okay, and then Friday will be your review day for the test on Monday and Tuesday next week. Okay?
Like grade present and then get bonus points?
Now you're going to get bonus points on the next quiz, not the test. Okay, so let's think. Anuj and Christian, you're new. Okay, so last year, and sorry, Megan, I had 3 in here. Last year we had free response days where we would practice free response questions like we've kind of seen so far on quizzes and tests. So we're going to do that tomorrow. One person from each group is going to come up and present either the whole problem or part of the problem, whatever I want you to do. And if you're the person that comes up here and presents, you get 3 bonus percentage points on your next quiz. So we have a test next week, but I'll put it on the next quiz that we have down the road. Okay? Okay. Now you guys choose in the group who comes up. I don't make you because it's voluntary, and that's why I give you bonus points. Okay? So up to you to determine that. All right. on page 225, we're going to take a look at, did we finish the airplane one?
Yeah.
We figured out how fast it was going?
Yep.
Okay. Next one. The radius of a sphere is increasing at a rate of 2 inches per minute. Find the rate of change of the surface area of the sphere when the radius is 6 inches. All right, so we're dealing with a sphere, which is like a balloon, and it says the radius of the sphere is increasing, so we're probably blowing up this balloon, getting bigger and bigger. And they give us a rate, they want us to find a rate, and it looks like they give us a point in time. So maybe we can label different things here. Can we label some variables in terms of this sphere getting bigger, increasing? What are some properties of that sphere that are changing or constant? Yeah.
The radius.
Radius, increasing, decreasing, or constant?
Like it's increasing.
Increasing, definitely. If the balloon gets bigger, the radius gets bigger. Any other variables?
Surface area.
Surface area, increasing, decreasing, or constant? Increasing. Now, if you read the question, it seems like those are the only 2 variables that we have. We could certainly talk about the volume of the sphere, right, how much air is in it, but notice how we don't really mention volume or a cubic unit. So even though that's a particular variable related to the scenario, it might not be one that's necessary. So you can list it if you want to, but don't feel obligated to use it in the problem itself. Can we list some rates? Rates that we know, rates that we want to find. dr over dt is 2 inches per minute. Now we said radius was increasing, so this will stay a positive 2. There's no need to make it negative. What about the rate we're trying to find?
Surface area.
Surface area. So dSA over dt, the derivative of surface area. We said it should be increasing, so we can anticipate a positive answer. What about our units? Inches squared per minute. Do we know a snapshot point in time? R equals 6. Okay, so if you were to take a picture while this balloon is increasing, the radius of the balloon on your snapshot would be 6. All right, so somehow we got to think of an equation. Our Geometric shape is a sphere, and we want to relate radius and surface area together. Typically, the equation will be given to you if it's like surface area, volume, something like that. But there are other ones that we have to know. For instance, we know the area of a circle. Maybe we'll write these down. Okay. We must know. Area of a circle. Pi r squared. Circumference of a circle. 2 pi r. Conveniently the derivative of area, right? If you bring the 2 down. Pythagorean theorem. Do we know it? A squared plus b squared equals c squared. What about the area of a rectangle or square? Length times width, base times height, whatever wording you want to use. Area of a triangle? 1/2 base times height. Volume of a cube? The side length cubed, okay. I'd say trig, also like sine, cosine, tangent ratios. SOHCAHTOA. I think we did a trig example yesterday, right?
Yeah.
Yeah, we got no trig. I'd say that's good. Okay, if it's anything other than these, they'll give you the equation. So can we find, in this case, an equation for the surface area of a sphere? Go to Noosh.
4 pi r squared.
4 pi r squared. Okay, before we get derivative happy, we got to make sure that the variables match the rates. We have surface area and radius in our equation, and we have the rate for surface area and the rate for radius listed. So it looks like we're good to go. Let's go ahead and find our derivative. We'll have dSA over dt equals, if we take the derivative of r on the right hand side, 8 pi r dr over dt. All right, so we took the derivative. We're going to focus on this one point in time, this snapshot moment. We're trying to figure out the derivative of surface area, so we'll leave that blank. Do we know the radius for a point in time? 6. Do we know the rate at which the radius is changing? 2. All right, so multiplied all together. 6 times 2 is 12 times 8. 96 pi. Units, inches squared per minute. All right, so that's exact. If you want to type it in your calculator, get a decimal value, you could go to 4 decimal places, but and trunk or round, whatever the case is. Yep. So there's our rate for surface area. Notice how it's positive like we anticipated, so I think we're good. All right, let's check out the last one. A spherical balloon. All right, we can't get away from these balloons. A spherical balloon is expanding at the rate of 6 pi cubic inches per second. How fast is the surface area expanding or increasing when the radius of the balloon is 4 inches? Kind of. Can we list some variables that are mentioned or hinted towards in the problem? Volume. Okay, we had that cubic inches unit. Increasing or decreasing? Or constant?
Increasing.
Increasing. They said expanding. Okay. Any other variables? Surface area. That'd be increasing. Radius. Increasing. All right, I'm pretty sure that's about it. Rates that we know or that we're trying to find. Yeah.
60 pi cubic inches per second is the volume increase.
volume increase rate. Okay, so dV over dt, cubic inches per second. Any other rates that we know or we're trying to find? Good, Christian?
We are trying to find how fast the surface area of the balloon is expanding.
All right, so dSA over dt. We said surface area was increasing, so we'll anticipate a positive answer. What about our unit? Inches squared per second. All right, I think that's good. Do we have a snapshot moment for this balloon?
Yes.
What is it?
4 inches for the radius.
Radius is 4 inches. Okay. So somehow we got to think of an equation dealing with a sphere again that involves volume, surface area, and radius. Do we have one equation that relates volume and surface area for a balloon?
No.
No. But we do have two separate ones, right? Okay. So can we figure out the equation for volume of a sphere, but also surface area? We already did surface area. That was 4 pi r squared from the last example. Volume of a sphere? Yeah.
4/3 pi r cubed.
Good. Do me a favor. Take the derivative of your volume equation. What do you get? 4 pi r squared, which is surface area. Wow. Okay, they're all connected. So let's check this out. We have two equations. This one's a little different, okay, because we've only been using one equation. But in order to relate all these variables together, it looks like we're going to have to use two. So for the first equation for volume, we have a V and an R, okay? Do we have those variables listed? We have V, but we don't have R, okay? Let's see, surface area, we have surface area and R. Do we have those listed here? No. Okay, so it looks like the R is the issue, so let's see if we can kind of get around that. Let's see, if we're trying to figure out the rate at which surface area is changing, we will have to know a dr over dt, right, to fill that in here.
Yeah.
So maybe we can use this equation to help us figure out dr over dt. That way we can plug it in here. Do you think we can do that?
Yes.
If we take the derivative of volume, dv over dt, and then the derivative of the right-hand side we said was 4 pi r squared dr over dt. Do we know the rate at which volume is changing?
Yep.
Yeah, that was 60 pi. Do we know the radius at this snapshot moment? 4. And notice how dr over dt is the only variable we have left. So we should be able to solve for it. 60 pi, 16 times 4 is 64. If we divide 64 pi over, the pi's will cancel. And then 60 divided by 64. We'll have 30 over 32, but 2 can go into those. 15 sixteenths. Okay, so at this point in time, during our snapshot moment, we now know the rate at which the radius is increasing. So maybe we can use that to our advantage to actually figure out the surface area rate. So derivative, dSA over dt, we'll have 8 pi r, dr over dt. We're trying to figure out the rate for surface area, so we'll leave that one blank. Our radius for the snapshot was 4, and the rate at which the radius is changing, we just figured out to to be 15/16. So 4 divided by 16 is 1/4. 1/4 times 8 is 2. 2 times 15, we got 30. 30 pi inches squared per second. There's our rate of change for surface area. All right, that one was a little different because we had to use those two equations, but still nothing I don't think we can't do. We doing okay? We're starting to get used to these. You see how they're the same process? It just depends on the equation and the shape. Okay? All right, we'll call it a day. Go ahead and try some homework problems. Ask for help if you need it. Get comfortable with implicit derivatives in these related rates.